So last week we have learned many things. We have completed chapter 3 already, how to start with stack and subroutine. So again, stack is the way we store data in the memory in the area that we call a stack, where we can put the data in the stack um, using the push instruction, and it is in the form of first in last out, yeah, where uh, when you put the data into the stack, the data will go to the bottom and the next data will go to the top, and then like this, yeah, the next data, the next data, and the next data. And if this is the last data, and the data will be stored in the stack uh, view like this. And when we want to take the data out from the memory, so the method is called the pop, where we get or retrieve the data from the top of the stack first. So last in, first out in this case. So the data last in here, first will go out from the stack. So the stack can be used to save the data, any type of data, or when we want to run what we call the nested subroutine, where we call the subroutine inside another subroutine. So we will need to save the return address, yeah, of the subroutine in the stack also, because remember we have only one LR register to store the return address. So in order to store more return address, when we execute many subroutine inside another subroutine, so we need to use the stack in order to save the return address. And we have learned this how to use the stack already last week, using the push instruction, the pop instruction to get the data back. And this will illustrate what is happening in the SP register when the stack pointer, when we execute the subroutine. So it will point to the stack address, always point the stack address, the top of the stack. For example, when we initially we set the stack address to be this address, right? So of course the SP will point to this memory location in the memory, which is the base address. And when we push the data into the stack, the data will be here, and it is automatically updated the address of the this the address to the SP register, right? And when I push another one, again the data is here, and the SP will point to the top of the stack, so that the next data will be here. And when we get the data out, so it will update it here. All right, this means that the next data to be popped out from the memory or the stack is this, right? When we pop, see, and then we get back all the data. And for the subroutine, so this is how we use the subroutine or subprogram in programming. So subprogram is actually just a sub part of the program, where we can use that lines of code or group of code many times by using the call instruction in ARM instruction set. The instruction to call the subroutine is called BL, the BL instruction. So for example, here we want to use this, we want to do this, and we can call this subroutine. So this is the subroutine name, and of course in your program you need to label or name your subroutine. Here subroutine 1, and this is the subroutine. And when we execute the subroutine, automatically the return address. What is return address? Means that the address that the microprocessor will need to go after you execute this subroutine. So in this case, the next address after we call this subroutine is this. and the address that store this instruction. All right. So whenever we want to go to this subroutine, we need to tell the microprocessor that after you do this, you need to come back and do this. Right. That is mean by return address. So the return address will be stored in the LR register, and after we execute all the instruction here, it will go back to this and do this and do this until finish. And this is how the things works. And you can check this using by running this program in the kill UVision. All right, and you can see all the addresses and the LR, the PC, and everything in kill, right? So you can try to do this, and this is what we call the nested subroutine, where we have the subroutine here, subroutine number 1, and this subroutine number 2 is called from the subroutine number 1 here. So in this case, we call this as a nested subroutine, where we call a subroutine inside another subroutine. And of course, again, when we call this subroutine, we need to keep this return address, the return address, which is the move instruction. The address of the move instruction need to be kept in LR register. But when we execute another subroutine during execution of this subroutine, so again we need to keep this stack no this return address, the return address of this pop instruction into the LR register. But we have only one LR register, so the previous value of LR register we need to save somewhere, and here is the need of using the stack. We save the previous LR value in the stack, so that we can retrieve it back later on. Right? That is how. So you can try to do this using kill microvision also, to see what happens when you execute this thing. Right? And we have do the example here. Yeah. How we communicate with the outside. And remember, we use microprocessor. Of course, we need to communicate with the outside, because we want to process the data actually. So, and of course, the data will come from the outside, from the keyboard, from the sensor, from the camera, or anything, right? So to communicate with the outside, we need to get the data from the outside, and the outside is called a port, through the port, the I/O port. All right. So this example demonstrates a simple I/O port. How is it works? Actually, it is mapped to the memory location in the microprocessor. So in chapter 4 later on today, we will learn in detail how this thing works, and what is the actual memory address for the I/O in the ARM microprocessor, especially for the microcontroller that we want to use later on. Okay, so that summarize the chapter 3. So we have learned a lot in chapter 3. We have learned how to execute, or learn how uh, uh, the instruction set work, how the instruction set work, what happened when we execute the instruction, and learn how to write the program in assembly language. And in chapter 4, we will apply what we have learned here in detail, and we will program our microprocessor using a higher level language, which is C++ programming, right, to develop a more complicated program. Okay, so that will be chapter 3. So welcome back again. We are now in chapter 4, which is the input, output, and peripheral of the microcontroller. So in chapter 1, 2, 3, we have looked at the microprocessor core and what is inside the microprocessor and how we communicate with the memory. And now in chapter 4, we will learn how to use our microprocessor to communicate with the outside. And we will use microcontroller in this case because the microcontroller is integrated with the I/O devices and peripheral already. No need to do extra uh, circuit design to communicate with the outside. But if you use microprocessor, in order to communicate with outside, you need to do to design an interfacing circuit, which is quite complicated, quite difficult, and of course time consuming. You need to design everything from the memory decoder, right? Design your memory and memory decoder and how to connect the I/O devices, the peripheral in with your microprocessor. But for the microprocessor, we have learned already in chapter 1 that everything is inside the chip. We just connect to the outside. For example, we want to connect to the keyboard, we want to connect to the LED, we want to connect to the LCD display. We just connect directly from the I/O pin of the microcontroller to the I/O device. But for microprocessor, it is not that way. You need to design the interface circuit before you can communicate with the outside. Right? So in this chapter, we will learn, we will use the microcontroller, which is the LPC 1678 microcontroller, which is based on M3 core, right? And it is manufactured by NXP, formerly known as Philip, right? And for that, we will look at what we call the memory map I/O. Right, we will see later what is memory map I/O, and we will learn the what is called the ARM embed. So the ARM embed is actually uh, the API, application programming interface, that will help the developer to build the prototype faster by using the pre or provided library, right? And in the ARM embed, we will look at how to use the what we call the digital input and output, how we read the digital data, how we output the digital data to the outside, and also we will learn how to read the analog input, because remember, outside is mostly the data is in analog. So and we want to use the microcontroller to process the data from the outside, and the data mostly in analog. So and our microprocessor is a digital electronic device, so we need to convert the analog voltage into the digital before we can manipulate the data or process the data, right? So we will learn how to read the analog input and how to convert that analog input into digital value, and also we will learn how to output the analog voltage from digital data. For example, we have digital data, we want to create the analog or change it to analog representation. We call it digital to analog conversion. We will learn that also, and we will learn what is called the pulse width modulation, or in short PWM. This is very good method to control in control engineering, to control the the devices outside there. So we will see what is this, and we will look at also the the advanced programming technique, how to design a good programming or good program, in the final part of this chapter. Right, so let's go to the first. Yeah, in chapter 1 we have learned the difference between the microprocessor and microcontroller already. And the microprocessor, we know already, it is a type of processor that is targeted for embedded system. Because the microcontroller, we have everything inside, even the ADC, the timer, the digital I/O, PWM, right, is integrated in the single chip, microcontroller chip, and we can use it straight away, and it is built for the small application, control application. So it is targeted for embedded application. What is embedded application? Means that the computer that is sit inside the electronic devices, right? For example, in our TV, we have microprocessor or microcontroller inside. In our washing machine, we have microcontroller that control everything, the operation of the uh, washing machine. Or even today, we have uh, in automotive industry, in our car, we have actually many microcontroller that control the operation of the car, braking system, right? Uh, uh, monitoring, monitoring system, right? All are uh, controlled by the microcontroller, and it is embedded inside the uh, the product. Yeah. For example, in washing machine, we cannot see the microcontroller. It is inside. It is embedded, right? It is not look like the computer, but it is actually a computer. Uh, in chapter 2, we have learned the ARM processor core architecture, right? That is widely used nowadays. Actually, this ARM microprocessor is more than 90% in the electronic devices, right? Especially in your handphone, in your tablet, in your smartwatch, right? And also in the uh, air conditioner, washing machine, TV, uh, internet or TV box, right? All are now using the ARM core processor, right? And we have also learned what is programmer model, which is the available resources that we use in order to write the program, especially in assembly programming, right? And in chapter 3, we have learned the most of the important instruction set, right? Where we use the what is called the thumb instruction set, which is the new variant of ARM instruction set, actually, the modern ARM instruction set, right? And we have learned how the microprocessor execute the instruction, right? And that help you to understand how the microprocessor works. So to understand how the microprocessor works and to know how to design a microprocessor system, the best way is to learn the assembly language, right? So we have done that in chapter 3, and in chapter 4 we will learn how to use or how to apply what we have learned in chapter 1 to 3. But again, the assembly language is important for space memory, right? Because assembly language is compact, very compact, very small in size, and of course, when it is compact, the speed is very fast when you write the program in assembly language as compared to writing the program in high level language. Uh, the speed of executing the assembly language uh, is very fast, fast as compared to the uh, high level language. Because when we write the program in high level language in C++, for example, we need to compile that code into the specific microprocessor. For example, if you use ARM microprocessor, the compiler will actually convert that C program, C code into the ARM instruction or ARM assembly language, and convert it to the machine language in order to be understood by the microprocessor. So of course, because the compiler, where it is sit on our computer, is a program that will convert that to the equivalent assembly language. So the program is uh, not optimized for speed. All right. So it depends on the compiler. If you have a good, very powerful compiler, you may get the very good output. But if the compiler is not that good, so the program may uh, be not that optimized. Yeah. And also it is power optimized. When you have your program in assembly language, because the number of liners is compact, is less as compared to the program in C, so of course it will optimize or reduce your power consumption. But the problem with programming or coding in assembly language is, first thing is that this, right? You have learned in chapter 3 already, to program in assembly language is hard, difficult, right? You need to know how the data is transferred from the memory to the microprocessor, how to move the data, how to manipulate, how to do the arithmetic, everything. And you need to know the hardware, the architecture of the microprocessor in order to use the assembly language, right? So this is time consuming and for complex application development. For example, you want to create the application that need to use IoT application, or reading a video, reading an image. Uh, so to program in assembly language is very hard, very difficult to do that, right? Because the program will be very, very long, and you need to do many things, right? So yeah, in practice, to develop that complicated application, we cannot actually use assembly language. We will use the C programming instead, right? But knowledge in assembly language is very important. When it's come to designing a very important part in the program, for example, that part of the application need to be executed or processed in very fast. So maybe that part of uh, process you need to optimize using assembly language, so you can actually mix assembly language with C, or to write the library. Sometimes we need to use assembly language, or maybe the hardware firmware, the firmware for the hardware, the use of assembly language is a better option, right? In order to get this memory, reduce memory, get fast speed, and also to reduce the power consumption. All right, so therefore, most application today, we will use the high-level language, and later on in this chapter, we will use the C++ programming in order to develop our program or our application. Right, from today, chapter 4 and to chapter 6, we will use C++ programming. All right, now let's go to the microprocessor that we want to use in this course, chapter 4, 5, 6. This is the specific microcontroller now, which is the LPC 1678. So when you search in the internet, there are many variants of ARM-based microcontroller actually. So this is one of them, right? Which is very, very popular, quite popular in embedded application. So this is the simplified architecture or block diagram of what is inside LPC 1678 microcontroller. So we have here is the core, the microprocessor core, which is the Cortex M3 core, which is the ARM microcontroller, actually ARM-based ARM architecture, right? This is the core, and this is the bus. AHB is at one high performance bus, and this is a bus also, peripheral bus, and this bus is connected to many things. You can see that here is connected to the SRAM, to the flash memory where we can store the application program here, right? And we have a connection to the Ethernet, yeah, direct access memory of the Ethernet. USB, we can connect to the USB. We have connect to DLL. We have I2C. This is communication. The peripheral. SPI also communication. We will learn in chapter 5. Right, I2S also the communication. CAN is also communication. We have ADC. This is analog to digital converter, which is inside the microprocessor or microcontroller as well. So we can actually connect the analog input to our microprocessor, microcontroller, and we can convert that analog input into digital data, right? And this is the size of this ADC is 12-bit and 8 channel here means that you can connect up to 8 analog input to your microcontroller. We also have the 10-bit digital to analog converter here. We have 4 32-bit timer here. We have PWM for motor control, or you can control anything actually by using the PWM signal, not only motor. So this is the PWM. We have encoder interface, right? And we have anything connected or peripheral. All of these are the peripheral that is built or integrated in the microcontroller, and we can use it straight away. This is the abbreviation for this ADC, which is the analog to digital converter, and so on and so forth. Right, now let's see how this microcontroller work, yeah, before we can use it. All right, so first thing first is that we need to know what is called the memory map IO. What is memory map IO? Here it says that memory map IO is the method of performing input and output between the CPU and peripheral devices in the microprocessor system. Okay, so that this is very important. So the memory map IO is the method of accessing, right, or communicating between the CPU, this, and the peripheral here. So actually, this peripheral is mapped to the addresses of this microcontroller processor core in the memory map. Here, remember this. This is the memory range of the ARM Cortex M3 microcontroller, where we have 32-bit address, right? So we will start at address 00000000 until the last address is FFFFFFF, which is 4 gigabyte in size here. So 4 gigabyte is huge, yeah. The memory is big for a microcontroller. And it is not used for storing data only, yeah. It is actually mapped to the IO or peripheral as well, right? For example, when we reserve this part, yeah, from this address to this address, means that we reserve this thing to what we call the general purpose IO, input output. And when we accessing this location, we actually access the IO. For example, here, this address 4003 4000. So when we access this any of this location, means that we access the ADC, right? So the memory map IO is something like this. If we can if I can draw here, we have the memory range from address 0 into the last address is 4 gigabyte for all F. Here, for example, in this case, let's assume that this is 2009 0000 is dedicated for the until so got range starting from this until for example 2009 0010 is dedicated for the ADC, right? Means that we have the ADC in the microcontroller, and this ADC has the internal register, just like our microprocessor. It has a internal register and internal memory. In order to keep the data, right? For example, the data from the analog input read into this ADC. When you convert the data from analog, of course, you get the output, the result in digital, and you need a register to keep that result, right? Internal register, which is for example 8-bit also, okay. And you also need to have many other register for setting or for controlling the operation of this ADC, right? So this internal register is mapped into this address in the ARM memory organization or memory map, as we know. So, for example, if we set and it is set by the microcontroller manufacturer. So, for example, this is this this register is mapped to, and this register is mapped to the next address, for example, and so on and so forth. Meaning that when we access using the instruction load or store str, right? Store str. Remember the instruction that we use to access the memory in ARM architecture or RISC computer microprocessor is using the load and store instruction. So when we load the data from this memory location, actually we load the data from the ADC like this. And when we store the data, for example, from our microprocessor core here, the microprocessor core here, when we store the data from microprocessor to this address, we actually store the data to the ADC, the register in ADC. So that is called the memory map IO. right? So this is IO devices, IO device. This is mapped to the memory of the microprocessor system. Okay, hope you're clear on that. So here we can see that we have many addresses that is mapped to the peripheral. For example, here from address 0 to address this one, which is in size is 512 kilobyte, is on chip flash, which is the location that we use to store the program, user program. And this one is reserved, which is means not used, not used. So you cannot access this location. You can read actually, but you cannot write. But read is no meaning, because this is not used. And for this 32 KB is dedicated for the RAM, and here is reserved also. This is 8 KB for boot ROM. This is for setup, when you power on your microcontroller. Reserve. This is SRAM, 2 blocks of 16 kilobyte. All right, this is reserve. This is GPIO. GPIO is general purpose input output. So normally we can use this for interfacing with any IO devices. IO device, for example, the switch, the LED, the LCD. Yeah, we can use the general purpose IO. Reserve, here we have SRAM. We reserve. This is peripheral 0, number 0. So here from this address to this address, actually it is huge, which is huge. So from here to here, this is when we zoom this part of memory location, we have many, right? We have watchdog timer, we have timer, we have UART, the communication, we have the PWM number 1, I2C, SPI, and so on. We will learn later in the subsequent chapter, right? We have ADC here, and many things, from this address 40000000 to the last address here, which is 40080000. This part. And we can see that this is another one, here, and this is another one here, right? Many. So, and all these are the memory of our ARM Cortex M3 or LPC, specifically this microcontroller 1678, and all of these peripherals are mapped to the memory in this. That means that whenever we want to access any of these peripherals, so we need to access the correct memory location in our program, right? So that is how. Now let's look at the GPIO, how to communicate with the simple IO device. For example, the switches, the LED for the output, switch is for input. So this microcontroller has 5 32 IO port, 32-bit IO port, and we name it port 0, port 1, 2, 3 to port 4. And each port is 32-bit, but not all bits are connected to the pin. So this 32-bit port, and remember this port is actually a register, a register, and the size for each port is 32-bit, and means that each bit here is connected to the IO pin of the microcontroller. For example, if I can show you here, if you can see, this is your microcontroller. So for example, this is the IO pin. All right. So this pin is connected to each pin is connected to each of the port here, yeah, bit here, right? This is bit number 0, we call it bit number 1 until we have bit number 31, and all of these are 32 bit. And not all of the port is or has the physical connection to the pin. For example, for port 0, bit number 12, 13, 14 is not connected to the pin. Means that we don't have any pin that is connected to this, or in other words, this one, this 3, and another one, this 4 are not available or not used. Not used. All right, means that you can read from this, but the value is not is meaningless, or you can write to this but you cannot send to the outside. And for port 1, yeah, we can see that bit 2, 3, 5, 6, 7, 11, 12, 13, yeah, does not have any connection to the pin, and the others are used, can be can is connected to the pin. All right, port number 2 only 0 to 13, yeah, connected to the pin. Port number 3 here, port number 4 only 2 bit, connect, has physical connection to the pin. All right, so you may ask why we have this, because this is actually because the IO, the size is big, and it is depend on the microcontroller manufacturer, yeah, whether want to use all the bit in the port or not. Yeah, in this case, in the LPC 1768, yeah, the manufacturer decided to have only this, because if you connect all the port to the pin, so you need to have many pin available in for your microcontroller. So let's see, if you have this one port is already 32 bit. If you have all the connection to the pin, so how many pin you need to have in your microcontroller? So your microcontroller will be very big, and of course the cost is very high. Yeah, so it is depend on the manufacturer, whether which one you want to create the physical connection to the pin, right? But the architecture is from the ARM, so ARM provide you to have all of this, right? But now, how do we use this port? How to use this port in order to interface with the I/O devices outside there? Uh, so first thing first is that we need to program or to tell the microprocessor what is the function of this port. All right, because this port is built or designed to be bidirectional, means that it can be configured as input or output at one particular time. For example, if we configure this as the input, or this part as the input, means that we need to connect this pin to the input devices, switches, keyboard. But if we configure this part to be an output, so we need to connect this pin to the output devices. For example, the LCD, the LED, the motor, right? So that is how we need to configure the port first. How to configure the port? We need to use another register in the I/O. Yeah, this is not in the microprocessor, but the register in the I/O. This is called the data direction register or the direction register. All right, and in ARM, in LPC 1768, the name is FIO DIR register. Right? direction register. Uh, it is 32-bit also. The register is 32-bit also, and one register is control has its control data direction register. All right. So for example, port 1 here, we have another register that control the data direction here. And the name is FIO DIR register. All right. So let's look at this. So for example, we have if this is our port and the size is 32-bit, so we have bit number 0 to bit number 31, and of course we need to have one if this is port 0, and we have another register called FIO DIR register or data direction register, and the name for to control the port 0 is actually FIO 0 DIR, and of course this is 32-bit also, and each bit here control the bit at the same location in the port. So for example, this will control the data direction here in port 0. This is port 0, right? And the now how to configure, for example, we want to set bit 0 in port 0 as an input. All right. We want to connect this to switch, for example. So we need to configure this bit as an input port. So the way is very easy, yeah, because this is digital storage also, and digital, of course, we have only two values that we can put inside here, which is 0 or 1. So if we put 0 here in this register FIO 0 DIR, so this will automatically make this pin or bit inside the port be an input bit or input pin. But if we want to connect this to the output device, for example, the LED, so we need to have 1 in here, and this will be the output. And if, for example, we want to connect or we want to create something like this, yeah, for example, if we look back to this chapter 3, we have something like this, right? We have the first one is no, here we want to connect to the switch, and here we want to connect to the LED, 8 LED. So maybe we can use port 0, where the first 2 bit is connected to the switches like this, and the rest, the next 8 bits are connected to the LED like this. So we can actually have something like this. We have bit number 0, bit number 1, 2, 3, 4, 5, 6, 7, 8, 9, for example. And of course, here we have exactly the same, the bit location. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So for example, with the first 2 bit here, we want to set as input because we want to connect to the switch. Right. So what we do is that we put 0 here, 0 here, and this will be input. And another 8 bit here, we want to connect to the LED. So we need to set this to output, to be an output. So to do that, we need to have 1 here, 1 here, 1 here, 1 here, 1, 1, 1. All right. So when we do this, all here will be an output automatically. Right. So now, whenever you read from here, means that, for example, if the value here is 1, means that the switch is pressed. Right. So how to read? You use the LDR instruction to read the content of register, and this port, remember, is mapped to the memory. So you LDR the memory location of this port, and then you get this value into the register, and you can know whether it is 1 or 0. If it is 1, for example, switch is press what to do. So for example, if 1, you want to on all LED. So what to do? So you just send 1, 1, 1, 1. This for LED, for example, or here still 0, and because this switch is pressed, so we on this for LED. So just send this value to the memory, use as tr instruction. And store means that we send this data into port 0, and when we connect this all to LED, it will turn on this for LED and off this for LED. Right, that is how the port work, or how we communicate with the outside, with the I/O. Okay, so this should be the same thing. So the data that is held by this pin, the port, is named as actually FIO PIN, pin. Okay, we will use this name to represent this port. So if port 0, if SIO 0, PIN. If port 1, if FIO 1, PIN. Right, that is the case. Now, because this 32-bit is actually big, 32-bit is actually big. So to access at one time we want to access 32-bit or manipulate data in 32-bit is quite a little bit difficult. So actually we have the option to manipulate the data in the 8-bit. That's why the LPC 1768 microcontroller have this option for us, so that we can divide this 32-bit into 4 bytes. We call it, do we have here? Okay, no, I just need to explain here. So we have the 32-bit register, which is quite big. 32-bit register, and we start with address 0 and with address 31. And we have the option actually to access this in 8-bit, where we can divide this into 4 bytes. Yeah, and we call it byte 0 here, where the bit is from bit number 0 to bit number 7. And we have byte 1 here, bit number 8 to bit number 15. And we have byte 2 here. This is from 16 to 23. And we have the last one is byte 3 from 24 to 31. Right? All are 8-bit byte, yeah, in byte. So if, for example, this is port 0, so to access this, or the name of this byte of port 0, we call it FIO port 0 PIN 0, means that byte 0. And for the byte number 1 here, this byte, we call it FIO port 0 PIN 1 to represent byte number 1. Byte number 2 is FIO, you can guess, port 0 PIN 2, and this one is FIO 0 PIN 3. And of course, we have the data direction register, which is the register that control or used to configure this every bit in this register to be input or output, is called the data direction register, or DIR. FIO DIR. And of course, for the first byte, byte number 0 here, the name is FIO byte 0 DIR 0. Here, FIO 0 DIR 0, and so on. Okay, now we want to know in the memory where is this, or this is mapped to what memory address, the specific address in the LPC 1768 microcontroller. So to do that, we need to actually open or have the user manual of this microcontroller. So you can go to the website, and in Google you can type for LPC 1768 user manual, and you have this. Just click this, and this is the manual. And for example, you want to know the address of this FIO 0 DIR 0, yeah, the actual address. So you can actually search for that in this, FIO 0, DIR 0, and here in page 134 of 851 pages. So here is the address of FIO DIR 0, 2009C000. This is the address mapped to this address. Means that whenever you store or read or load value from this address or store to this address, means that you actually accessing this port 0, byte number 0 of the GPIO port, right? Means that you accessing this. And when we look at here GPIO, and starting from this address 2009C000 is actually yes, GPIO 0. See? And the first address is actually mapped to this FIODR 0. And what is the next one here? This is FIO1, means it's port 1 byte 0. So this is port 1 byte 0, and this is mapped to 2009C020. See? So within this one, C020 is actually data direction register for byte 0, port 1 here. So for port 1 is actually the next address. You see C000. C001 is actually for byte 1. So if we look at this the address for this is because remember in our memory one location is actually 8 bit. Yeah, one location is 8 bit. So the first not the first, the address this is actually the FIO 0 DIR 0, means that port 0 byte 0 of port byte 0 of port 0. And the next one is 9000. C001 is actually FIO 0 DIR 2, 1. Yeah, DIR 1 here. See, DIR 1 is C001. DIR 2 is the next one. See, 2009 C002 is the next one. The next one. This is the memory map IO, where we map every location here to the IO. Right, so let's come back to this. So now, what if we want to access or the name of port 2 byte number 3, for example? Let's, for example, we want to know where is port 2 byte 3. Yeah, what is the name? So the data direction register is FIO port number 2 DIR 3, and the pin is FIO 2 PIN 3, right? So when we want to know the address, we need to open the manual and try to get here is actually 2 byte number 3. Where is it? Here. The address is 2009 C043. This is the address 43. So the address is 9000 C043. And for pin, the address is, change this to PIN. We have 57 9000 C057 is actually port 2 byte number 3. Port 2 byte number 3. Where is byte number 3? Should be here. And this is not used actually. Okay, so that is how we access the port, yeah, using the addresses in our memory. And here is the example how to access the port. Yeah? So yeah, FIODIR0 is this one. This is the same example. Same thing here. This case. So if we look to this, this is FIO0. This is port 0. DR0, byte 0. Yeah, 1 byte, 8 bit, 0 to 7. And the address we know already, which is 2009 C000. And for example, we want to set this as input, this 4 bit, 4, 5, 6, 7 as input. Of course, we need to put 0 in here, and we get the input here. And for example, the next 4, we put 1, 1, 1, 1. So here we will get the output. And the address for FIO0, yeah, port 0, pin 0, byte 0 is this, 2009 C14, C014. Exactly this, C014, yeah, FIO0, PIN 0. And this is the port and associated pin on the LPC 1768. So let's find this pin. Pin number 0 in port 0. Yeah, this pin, yeah. So in this, we need to look at this, the label here. P1 means that port 1, right? Port 1. So port P1 dot 0 means that this is port 1, bit number 0. So to find port 0, we need to look at P0. Where is P0? Here is P0, bit 0. So this is, yeah, this is the pin. Pin number 46 is actually connected to this pin. Yeah, has wire, physical connection to this register, this bit. The address is 2009 C014, bit number 0 is connected to this. What about bit number 1? This is bit number 1. Port 0, bit number 1. Number 2, 3, 4. But here it is not represented in byte. It's represented in 32-bit. So we can see, for example, in P1 here, it started from 0, 1, 4, 8, see, until P31. This P31, P1.31 means that this one is port 1, bit number 31, which is belong to byte number 3, right? Byte number 3. And we can see that for P3, for example, if we find P3, we have only two bit that is available in at the pin. So when we look at here, we don't have any P3, we only have P3 for two pin, which is pin number 27, 26, and this is mapped to or connected to bit 35, 25 and 26. So if we look at this, yeah, port 3 is connected to 25 and 26 only, and here port 4 we have 28 and 29. When we look at here, we have only P4 28, 29, and we don't have any P4 available here. Means that there is no connection, we cannot use. All right, so here is the program example. So before we go to the program, we have a short break, maybe 5 minutes, yeah, and come back to here and see the program. Okay, we have 5-minute break.